Hello friends, in the previous video we have already covered four categories of operators: arithmetic operator, unary operators, assignment operators, and conditional or relation, or we also call it comparison operators. Okay, and at the time I told you that before going further we need to have some prerequisite knowledge so that we can properly understand the logical bitwise operations in Java, and further operations also we will cover later in the next video. But this video is about that prerequisite knowledge. Okay, and that prerequisite knowledge is about how to understand or communicate with computer in its machine language form. Let's say if you're going to Germany and you're going to work in that company which is in Germany with German people, so you are going to learn German language, right? So similarly, now that you are going to work with machines, okay, you are going to program for machines, so you should know how machines will interpret your language or your words or numbers, right? So that's the point here. So far we have always been doing all the mathematics using the decimal number system, okay, which goes like from negative infinity, -9, -8, 7, 6, 5, -1, then 0, and then positive numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and positive infinity. Okay, but your machine will not understand them like this. Okay, the machine will always interpret it into the binary number system, also known as bit representation. Okay, I have given some examples in 8-bit representation format here. This is on the left side you can see the decimal numbers. On the right side you will be able to see the bit representation or binary number system representation. Okay, and how to convert the decimal numbers into the binary numbers, so that we will learn here now. Okay, now let's say we have to convert 7 into a binary number. Binary means where we have only 2 bits. Okay, so we will always divide by 2 for whatever the number that we have to convert from decimal to binary. Okay, so 2 and 7 here. Okay, now 2 3 times is 6, the remainder is 1. With the color code you will understand the 1 will go on the right side here in this column, the third column. 2 will go in the leftmost column, okay, the first column, and 3 will go below the 7. Okay, so now from here we can say that in this column we always are going to have 2. Okay, in the middle column we are always going to have the number which we want to convert. On the right column we will have always either 1 or 0. Okay, either we will have 1 reminder or 0 reminder at the end, right? So that's why we will have either 1 or 0 here. Okay, now in the middle column, as soon as we get 1 at the end, okay, this is where we have to stop dividing. All right, now 2 3 times is 6, remainder is 1. 2 1 times 2, okay, then the remainder will be 1, and now we got 1 here, so we'll stop, and we will read the binary number system from bottom to top. So that's why it becomes 1 1 1, but this is only 3 bits. Okay, to fill it into the 8 bits we have to fill it like this. Okay, so whatever the remaining bits are, we will fill them with 0. Okay, 0 0 0 0 0 1 1 1. Okay, let's try one more time with another example. We will convert 8 now. Okay, so 2 4 times 8, remainder is 0. 2 2 times 4, remainder is 0. 2 1 times 2, remainder is 0. Now we got 1 here, we will stop here. We will read it from bottom to top again. 1 0 0 0. We have 4 bits. We will fill the remaining 4 bits with 0. Okay, so 0 0 0 0 1 0 0 0. So this is the 8-bit representation of 8. Okay, let's try one more example, but this time you will tell me what will be the binary representation of 13. If you have got the answer for this, please comment below so that I know that this video is helping you to learn more. Okay, let me tell you what will be the binary representation now. So 2 6 times 12, remainder is 1. 2 3 times 6, remainder is 0. 2 1 times 2, remainder is 1. So the binary representation 1 1 0 1. So it will become 0 0 0 0 1 1 0 1 for 8-bit representation in binary format. Okay, so this was about how to convert from decimal to binary numbers. Now that we know the positive numbers, we also need to understand how to get the binary representation for these decimal numbers. Okay, alright, so for that you have to follow 2 steps. The first step will be invert the bits of positive value. Invert means you will convert 0 into 1 and 1 into 0. And then once we have got the inversion result, we will add 1 into that result, inverted result. Okay. Let's try with an example. So we have 5. The 5 is represented as 00000101 for 8 bit. Okay. We need to find the binary representation of -5. Okay. So step 1, inverting the bits. So all the zeros will become 1 and ones will become 0. Okay, so this will like 1 now is 0, the 0 is 1 and 1 is 0. So we have got the inversion result or inverting result for 5. Okay, now the second step, we have to add 1 bit to the result. So this is the result. We will add 1 here and 1 is represented like this in binary. Okay, so 1 plus 0, 1, 0 and 1, 1. Similarly, we will add other bits and we will get this as a result. And this is how we represent -5. Okay, in binary format. Now that we have learned the whole number system in binary format, we will start for operations. Okay, how to perform different logical operations in bit or bit representation. Okay. Now we have these categories of logical operations: AND operation, OR, NOT, XOR, XNOR, and shift operation. And the shift operation can be further classified into signed left shift, signed right shift operation, and unsigned right shift operation. Okay. Here, similarly, we can have unsigned left shift also, but we will just try to understand this only for now. 6.1, this is 6.0. So let's try with AND operation. So for AND operation, whenever all the bits are 1, then only it will be 1, otherwise it will be 0. For example, 0, 0. So all of them are not 1, so it will be 0, 0 and 0, 0, 0 and 1, 0. Why? Because there is at least one bit that is 0 or not 1. Then 1 and 0, again we have one bit that is not 0, so it will be 0. 1 and 1. Now that we have all the bits, or we can say both bits as 1, that's why it will become 1. So that is the rule in AND operation, that all bits should be 1, then only the result will be 1, otherwise it will be 0. For OR operations, at least one bit should be 1. Okay, then it will then the result will be 1. All right. So 0 or 0, we have 0 because none of the bits is 1. 0 or 1, it will be 1, at least 1. Okay, so we have one bit available, so we will be using 1 as result. 1 or 0, 1, 1 or 1, 1. All right. Now we have a NOT operation. We also call it as bit inversion. Okay, so NOT of 0 is 1, NOT of 1 is 0. Okay, then we have XOR operation. So in XOR operation, what happens whenever two bits are same, or we can say two operand bits are same, the result will be 0. But if two operand bits are different, the result will be 1. So 0 XOR 0, both are same, it will be 0. 0 XOR 1, both are different, it will be 1. 1 XOR 0, 1, and 1 XOR 1, 0. Okay, why? Because both bits are same. XNOR, it is nothing but NOT of XOR, NOT operation on XOR result. Now NOT means inversion, so 0 will become 1, 1 will become 0. That way we will get the output for XNOR operation. So 0 XNOR 0 is 1, 0 XNOR 1 is 0, 1 XNOR 0 is 0, 1 XNOR 1 is 1. We can also understand it this way, that if both bits are same, the result will be 1. If both bits are different, the result will be 0. Now let's try shift operations. Okay, so we will start with the signed left shift. Okay, for example 3, this is the operation of left shift. Okay, so 3 left shift 1, that means we have to shift the binary representation of 3 by 1 position. Okay, how many positions? We can do anything like 3 positions at the same time, or 5 positions, whatever. So for understanding it in a simple way, I have put only 1 position shift. So 3 is represented like this in binary representation. Now we have to shift it one time to the left. That means this one will go here, this second one will go on the left bit side. So that way, and the rightmost will become 0. Okay, the rightmost bit will become 0 because we have to fill that bit. Okay, and we always by default fill the bits by 0. Okay, now that will be preserved. The second leftmost will be removed. Okay, so that is how the signed left shift works. This 0 is not shifted, but this 0 is removed and the other ones have been shifted left side. Okay, why this has not been removed? I am saying if it was 1, that means the number was negative. There was some negative number, so this signed bit will be preserved. Okay, we don't shift it in signed left shift representation. All right, this you need to understand clearly, but we will have more understanding when we are using the signed and unsigned right shifts. So let's try to understand again. So we have shifted all the bits to the left, removed the second leftmost bit and kept the leftmost bit, okay, as it is. Now we have got 110. You can see this 110 means 6. Okay, this means 6. I already explained it like this here. So this is 6 is that, so 3 left shift 1 position will give the output of 6. Signed right shift, so we have to shift 1 position to the right for 3. Okay, so this leftmost 0 is the sign bit. We won't do anything with this, and we will shift all this value on the right side to 1 position. This 1 will be removed, this 1 will come here on the first 1 position, and the filler will be again 0. So it will become like this, and the output will be 1. Got it? Let's try one more thing. Okay, with -3. Let's try the same example, signed right shift with -3. Okay, now you already know that 3 is represented like this, so -3 will be represented like this. If you don't understand this, again follow the 2 steps that I told you how to convert a positive number into negative number. So follow this and you will get the same result of -3 also. Okay, so let's try 1 position shift for -3. Again, this 1 will remain as it is. Okay, the other will shift, all the bits will shift on the right side to 1 position, and there will be one gap here. That gap will be filled by 0. Got it? So this has been shifted here like this. Now if you will see the representation of this number into right shift, so the result will become -1. All right, let's try with the unsigned right shift. Again 3 right shift 1 with unsigned. Unsigned means now we don't need to keep this as it is. Okay, this is also unsigned, so this is not a signed bit. Now this is also part of the other bit representation, so we will shift all the digits. Okay, and the 3 will be 1. So when we are working on unsigned right shift, the result will always be same like signed right shift for positive numbers, but for negative numbers it will become different. Let's see how. So this is -3, -3. If we shift all the values, I already told you for unsigned we don't need to keep it as it is. We will shift this also and we'll put the gap as 0. Okay, we'll fill the gap as 0, and this will be converted to decimal as 126. Okay, you might ask like how do we convert binary representation into the decimal representation? That I will tell you in the next step. If you want, you have to comment that in the comment section if you want me to explain that also. Now that we have understood all the operations and number system, binary number system, and converting decimal into binary, that is machine code, so we are ready to go to the next video, which will be about the operations that we had to cover: logical operator, bitwise operator, and then we can try few more operations like ternary operator and instance operator. Okay, so I'll stop the video here. If you have liked the video, please like and subscribe to my channel. Thank you for your support.